So, hello everyone. My name is Shourya Mukherjee, and I'm a student here. I'm with Space at VT. I'm currently working on my PhD under Dr. Scott Bailey, and my topic is about polar mesospheric clouds or PMCs. And specifically, I'm working on the influence of long-term effects of space traffic, which is launches, on PMC frequencies. And in this, I'm also working closely with the science team of the Aeronomy of Ice in the Mesosphere or AIM satellite team, and which was a satellite dedicated to studying PMCs. So I'll begin here. Yeah. So what are NLCs? Now, PMCs were initially known as NLCs or noctilucent clouds, uh, popular in context to ground observations mainly. So that's because to a ground observer, these clouds mainly appear after sunset at latitudes poleward of 60 degrees in both hemispheres. So after sunset, hence nocturnal, and they have a bluish white glow, hence they're luminescent, so noctilucent clouds. Now,
You here for the seminar?
Yes.
Yeah, join us, yeah.
Okay, I just didn't want to interrupt anything important.
Oh, no,
you're right.
yeah, so these clouds appear in the mesosphere during the summer seasons. A PMC summer season is roughly between May to August in the northern hemisphere and November to January in the southern hemisphere. So during this time, the temperatures in the mesosphere drop to as low as 140 Kelvin, which is the lowest in the atmosphere. So that provides an environment for formation of microscopic water ice particles, which PMCs are comprised of. And since these are much smaller than those of the common clouds, these appear very thin and wispy, as you can see in the diagram here. So due to this also, these particles are extremely sensitive to small changes in the mesospheric temperature and water vapor. And due to this, though it was debatable for a long time whether PMCs actually influence climate change, they have been considered, there's a consensus that they are useful indicators to track global atmospheric dynamics, climate change, and such phenomenon. Now, PMCs display a variety of patterns, some of which I've listed here. Uh, they were observable through ground observations. Most of them are similar to the common clouds. And since satellite measurements started, particularly with high resolution imaging of the CIPS instrument on the AIM satellite, we uh, have observed many unique structures also, which were never seen before in PMCs. Now, how do these clouds form? So NLCs, since they are so high up in the atmosphere, in the mesosphere, much higher than the common clouds, these always receive direct sunlight, even when the sun is below the horizon. So the light passes much uh, away from the horizon to the clouds. So they always exhibit Rayleigh scattering, which, as you might know, it predominantly reflects blue light. So that's why it appears bluish to an observer from the ground. At night, they are distinguishable by their color and glow, but in the morning, they're hidden by the more common clouds, really. So they're visible more at night. The image below is an observation from the CIPS instrument on the AIM satellite, and this is how they look from space. So when viewed from space, NLCs are more preferentially known as polar mesospheric clouds, which is more representative of their properties, really. Now, this is an image of the general circulation processes that take place in the atmosphere. So during the summer, upwelling of air masses occur, which is the upward motion. So when an air mass moves towards the high altitudes in the mesosphere, they expand and cool. It's a process known as adiabatic cooling. And this is mainly responsible for the low summer mesosphere temperatures. Due to upwelling, also, air masses full of water vapor reach the mesosphere, and that increases the water vapor content here. And this low temperature and high water vapor, they are conducive to formation of PMCs. Now, ever since industrialization started roughly around the 1960s, several studies have consistently reported that these clouds have been increasing. So one study by Dr. François Lupkin showed a drastic difference in the trends pre-1960s versus post-1960s in atmospheric temperature and water vapor. And that was also reflected in the PMC measuring parameters. Now, what happens when greenhouse gases increase, among them carbon dioxide and sometimes ozone, they exhibit radiative cooling. So what they do is they absorb radiation from the lower layers and they radiate it out into space, skipping the mesosphere, so that lowers temperatures here further. And methane, they react with atmospheric oxygen to produce water vapor, which increases water vapor. So increase in greenhouse gases have been seen to accelerate the process of lowering temperature and increasing water vapor. So they help in forming more PMCs. So this, combined with the high sensitivity of PMC particles, they make them great analysis tools to understand both natural and anthropogenic changes in the neutral atmosphere. Now, these are some factors which are known to affect PMCs. Some of them we discussed earlier. And among others, there is the solar cycle, which is known to inversely affect PMCs. So during a solar maximum, the temperatures in the mesosphere increase, which help reducing PMCs, and vice versa. Volcanic eruptions are also known to affect PMCs locally. They may either raise atmospheric temperatures and reduce PMCs, or if it's an undersea volcano, it can also inject a huge amount of water vapor to potentially create PMCs. Now, atmospheric coupling is the influence of, roughly it's the influence of dynamics of the stratosphere on the mesospheric dynamics. So it mainly affects the circulation pattern and the temperatures here, which indirectly can affect PMCs. So this can happen in the same hemisphere, which is known as intra-hemispheric coupling, or it can affect the mesosphere of the different hemisphere, called inter-hemispheric coupling. Teleconnections are also kind of similar to coupling. It just happens between places which are much distant. And waves and tides are also known to affect PMCs as they create some disturbance in the formation. I can't go into much details on this. But yeah, so my focus is on space traffic effects, which is an anthropogenic source mainly. So what happens? Shuttles and rockets, their exhaust plumes contain several tons of water vapor, which during launches are injected into lower thermospheric altitudes, from where they descend through processes like sedimentation to mesospheric altitudes to potentially form a reservoir of water vapor that can create PMCs. So I'm studying on what the extent of this reservoir in creating PMCs and affecting the interannual variability of the clouds. Now I'll briefly talk about some physical quantities that PMCs are measured with. The first two bullets are just self-explanatory. I've added them because several ground observations have studied trends of the mean altitude of these clouds and their extent. Now, a property of the cloud which measures the proportion of incoming radiation that is scattered and received by satellites is the volume scattering coefficient. And from this, PMC albedo can be calculated, which is often used to measure PMCs. So albedo, as you might be knowing, is the ratio of outgoing radiance to incoming irradiance. And it is a directional quantity. It is dependent on the viewing angles and the orientation of the satellite. So it's kind of challenging to measure, to compare different instruments with albedo. But there are several PMC retrieval algorithms which depend on the instruments. These are very detailed algorithms which can compute the more bulk properties of the clouds from albedo and volume scattering coefficient. One of them is the ice mass density, which is basically the ice mass per unit volume. It's the density of the ice of the cloud. And from there, a very important quantity called ice water content is computed as vertically integrating the IMD over a PMC column, like I tried to demonstrate here roughly. So ice water content is important in that it represents the amount of ice in the cloud, and it's a measure of how bright PMCs are. And this being a property of the clouds, ice, it is expected that it will have much lower instrument dependence and it makes comparison easier. And total ice is just the amount of the mass of cloud ice in a region. It can be computed as the product of ice water content and the field of view of the satellite. Now, apart from these, there are also certain microphysical quantities which are more the properties of the individual ice particles. But PMC microphysics, it's a very deep area of research, so I can't go into much details. I'll just say that these pertain to the size, shape, and concentration of the ice water particles in PMCs, and also the nucleation rate, which is how fast the cloud grows due to accumulation of ice around particles like meteoric smoke or aerosols. That's how the particles form. The particle size distribution is a probability distribution of the particle radii. It is found to be Gaussian in shape for most studies, but this also depends on the type of study and the type of instrument, the analysis methods, where other fits can also work. So these parameters are important in doing studies like common volume studies, which is about the studying the extent of agreement between different PMC measuring instruments. They look at the volume which both the satellites observe commonly, and parameters can be calculated there. So there are many recent papers on common volume studies too. Now, I mainly work with occurrence frequency, though I've worked with ice water content before too. Now, occurrence frequency, the definition is very simple. It's the ratio of the number of clouds to the number of observations. And I've tried to put a sketch which roughly explains that. If you observe a certain number of clouds over a time period, we can calculate it as the percentage of observed clouds. So by number of clouds, we mean the number of cloud pixels observed in the satellite field of view. So depending on how these pixels are interpreted, which might depend on the viewing altitude, the threshold of albedo taken to mark if the PMC albedo is higher than that, it's considered as a detection, or how the satellites view, whether it's limb or nadir viewing, it depends on all that. So frequencies calculation varies with that. And frequency also depends on the chosen time and spatial scales. So some caution is to be taken here that when we are considering a particular region, we have to add up the clouds and observations for each such region and compute the frequencies accordingly. So yeah, overall, this is an easy parameter to work with. It measures how frequently clouds appear. So it's useful in analyzing how the clouds increase or decrease over time. Now, PMC parameters are often measured separately in two halves of the orbit, known respectively as ascending and descending nodes. I've mentioned there. So that's because due to the time it takes to orbit, at a particular latitude and day, these 2 points can be at 2 points of observation can be at widely different local times. So as an example, I've shown that plot here. This is a study done by Dr. Michael Stevens. He showed that in the green portions, which is the latitude bands between 65 and 75 degree north, and the red dots are the PMCs detected. So as you can see, at 4.7 local time, there are much more PMCs than 13.2 local time, though the latitude and the day are the same. So this is an example of an early morning bias because there are more clouds in the morning. So such biases may exist. So in studies where inferences depend on local time, it's important to consider both the nodes separately. Now, studies have also shown that at higher latitudes, this dependency is almost negligible and it's more prominent at low to mid latitudes. Now, these are some studies which showed that space traffic do create PMCs. All those mentioned here are shuttle-based studies. So in the top image, it is a observation made from the Poker Flat Research Range at Alaska on August 2005. It shows that there was a sudden burst of clouds that appeared on 1:30 local time on that day. And the corresponding plot is at the bottom left. That yellow-red region, it shows the sudden spike in albedo, in PMC albedo at 1:30 local time. So this was known to appear approximately 10 days after the shuttle launch, and it also lasted for 10 days more. A similar observation was made on August 2001 also, and they were compared to other seasons where there was no shuttle launches, and the densities in these seasons were found to be almost double. So that's very significant. Now, other studies also showed that how exhaust plumes from shuttles can be transported over long distances to form PMCs elsewhere. And there's a study on mid-latitude by Dr. Stevens in 2022. He showed how there can be a dependency of the launch local times, where he showed that restricting the launches to a range of times has the strongest correlation between number of launches and frequency. Now this plot on the bottom left, this is a study done by Dr. Matthew Dillon and Dr. Gary Thomas. The bottom plot is the descending node. I hope it's visible. This part I'm talking about, this part where in this launch, after this shuttle launch indicated by the vertical line, there's a steady increase in cloud frequency for a few 4 to 5 days. But such a rise was not observed in the top plot, which is in the ascending node. So this showed that PMCs effects, shuttle effects on PMCs can be more localized. Now, these are all shuttle-based studies. Dr. Dave Siskind in 2013 was the first to point out that these effects can persist beyond 2011 when the last shuttle was launched. So other launches might also cause this. And he has shown it with respect to solar cycle mainly. So unusually in the later years, the solar cycle maximum doesn't seem to affect the PMCs so much. The PMCs are still increasing. So he has shown evidence that it can be due to launches. Now, this is a compilation of some news articles and some research papers I found that talk about space traffic effects. The key takeaways are in the blue boxes. It just talks about how a launch in Florida, the plumes from there was transported by winds to Texas and PMCs were formed there. They were observed really, and Texas is much lower than the 60-degree latitude. So PMCs formed artificially can appear at low latitudes and also away from the poles. Now, we also know that since 2008, the number of launches have been quadrupled. So there are going to be more launches, and PMCs have also been increasingly observed. So we are just going to see more space traffic effects. So this research area can become popular. Now, this statement here, you see at the bottom, my first study is based on this a lot. So this was observed by Dr. Stevens, who has worked with me in my research too. So he showed that the total amount of water vapor transported is more instrumental in modulating the PMCs and not the vehicle size. So it doesn't have to be a large vehicle like a shuttle. If there are a large number of launches in a particular year, the combined water vapor can also modulate PMCs. So I will just very briefly talk about the instruments I use data from. So the top 3 images are respectively the cloud imaging and particle size of CIPS instrument, the Solar Backscatter UltraViolet or SBUV2, which is an upgrade of the initial SBUV instrument. And then we have the Ozone mapping and profiler suite, which is another more recent instrument which provides SBUV consistent data. So for my first study, I use data from CIPS. It's a very high horizontal resolution instrument, so it can measure clouds over a wide range of brightnesses from the very dim to the very bright clouds. SBUVs, on the other hand, have a much coarser resolution. That's mainly because it was not intended to measure PMCs initially, but from its ozone and stratospheric profile data, PMC parameters were calculated. So these can detect only the brightest fraction of PMCs, and the dimmer frequency are rarely visible. So now all of these are nadir viewing satellites, and the middle image just shows the 4 CIPS, the 4 cameras that CIPS has. It can view PMCs at multiple viewing angles. So the field of view is much larger for CIPS than SBUV. And OMPS has multiple configurations. Among them, I'm using data from the nadir profiler configuration because it's nadir viewing. And for my second study, I use SBUV data because it has a much longer timeline, and I'm seeing clouds there for a longer data. The timeline I've shown in the plot there. So as you can see, not all the instruments observe data continuously, but combining them, as they've been shown to be pretty consistent with each other, the SBUV and OMPS instruments. So we have a continuous and overlapping data from 1979 and still continuing. These are a source of data sources I've used data from. Now I move on to my first work. So in this study, I'm trying to investigate the bright clouds, PMCs observed by CIPS. I've tried to investigate the effects of space traffic on these clouds at 80-degree north latitudes over the period when CIPS was active from 2007 to 22. So the approach we take here is I try to find a range of local times in which the correlation between the annual number of launches and the PMC frequency at 80-degree north averaged over July because it's the peak of the season and I want to look at the brightest clouds. So the correlation for what range of local times this correlation is maximum, the strongest. And after I do that, I use wind data from the Icon MIGHTI instrument. And also to see if they agree well, we use meridional wind data from simulations from HWM14 model. And with this, we want to show that at the same local times, whether the wind velocities are favorable in carrying the plumes northward to our desired latitude. We also use temperature and water vapor data from the microwave limb sounder on the aura to find that for these brightest clouds that we are seeing at this latitude, which one is more instrumental in modulating the variations? Is it temperature or water vapor? And combining these inferences, we try to explore the causality and not just the correlation. So we don't do the correlation only. We use wind and temperature, whatever data to show evidence for that. Now this is the plot of the seasonal frequencies. Each curve represents the season from 2007 to 22. We use an albedo detection threshold of 6 units, which is widely accepted by the AIM science team as the standard CIPS brightness. So the solid lines here are the July frequencies. So if you see that the interannual variations are very prominent here, even though the frequencies are near maximum in July. So to investigate these more, we choose the July frequencies only. Now, after we do this, we average the frequencies for each season and we create a time series, an interannual time series. So we do this for the ascending node and the descending node separately first, which is the black dotted and the dashed lines here. And say, as you can see, it's a high latitude and the frequency are very close and highly correlated. So it gives us confidence to combine these two measurements by adding up the clouds and observations in both the nodes. And that's the black solid line. We will use this here from now. I also show the mean observation local time in the ascending node and the descending node, which is the red curves here, the dashed and dotted respectively. It's just to show that there is no appreciable dependency of the interannual variability on the local time. As you can see that there's no variation such observed. Although in the later years, the time shift to the morning, which is also followed by an increase in the PMC, the overall PMC frequency, if you compare the first half to the previous half. Now, we don't have any data for 2017 due to instrumental issues. So that place is blank really. So yeah, we will revisit this increase in frequencies in a later plot. So now we correlate the annual number of launches and the frequencies here. The red curves are the launches. So we count this in two ways. So first we take all the available launch local times and we count them per year with all local times and we get a high correlation coefficient of 0.6. Then we repeat this by constraining the local times in this window 2.5 to 1.5. And how we got this, I will explain in a bit. But with these local times, we found the correlation to improve slightly, which indicates the weak local time dependency at high latitudes too. Another important observation here is in the later years, the number of launches is also increasing. The clouds are also increasing. So that's also an evidence. Now, here we choose this window. We also varied the window over a diurnal cycle, and we calculated the correlation coefficient at other ranges of days and local times. And these plots you see here are the sweeps. So the top plot, here in the top plot, we vary the days of launches and compute the correlation coefficient. So we keep the width of the window fixed at 1 month, and we sweep it over June and July, and we find the highest correlation at a window corresponding to 26 June to 26 July, which is interestingly 4 to 5 days before July. So it kind of indicates that there is a 4 to 5 day lag for the exhaust plumes to reach the latitudes. Now, once we fix the days here, we also do this on local time. So we initially fix the local time window width to a chosen value, and we sweep it over a diurnal cycle, and we find the maximum correlation at 12 hours at a window centered at 12 hours. Now we fix it at 12 hours and we vary the width. And we find the highest correlation at a width of 19 hours. So combining this 12-hour center and 19 hours width, we find this window of 2.5 to 21.5 local times, which is a really wide window, but it still improves our correlation coefficient. We also vary the R value, which is the correlation coefficient, over different albedo thresholds, that is different ranges of brightnesses of clouds. And we find that to be relatively insensitive. So the correlation is always pretty much above 0.68. So this just tells us that it is applicable for other brightnesses too. So these maxima provide constraints for the launch day, range of launch dates and local times for which the correlation between launches and frequency is the strongest. Now, once we have our window, we list all the launch sites within that window. We found a total of 97 launches. We note their latitude and the number of launches per site. Using this information, we compute something called a weighted average latitude with this equation given here. Now, with this latitude and number of launches information, we calculate this weighted average latitude to use wind data on it to check if an air mass traveling from the weighted mean latitude propelled by the wind velocities, can it reach the desired latitudes we want? So we do this again in two ways. Because we use wind data, we refer to another research which showed that meridional winds are very weak equatorward of 10 degree north. So we also calculate the weighted mean, excluding the launches which are below 10 degree north. So this table is for our maximum window for maximum R. We calculate them for the other windows like we did for the sweeps. So that's the plot in the second panel. That's the weighted mean latitude in the solid line for the sites north of 10 degree north. And the dotted line is for all the sites. We do the computation for both cases. The top panel shows the wind velocities. The black curve is the instrument measured velocities by Icon MIGHTI, and the magenta curves are just different chosen latitudes simulated by the HWM14 model. And we don't use this in our computation. We just want to show that the velocities agree well. So we average the velocities over our chosen days, June 26 to July 26, and also between altitudes 100 to 109, because that's where the injection is known to occur, injection of the plumes. So using the information in the first and second panel, we use a parcel advection algorithm where we move an air mass north of south from the corresponding mean latitude. And we see that due to the wind velocities, how far northward it can reach. So this computation is shown in the third panel. This black curve is for the north of 10 degree north sites, and the dashed curve is for the all sites. We have overplotted the correlation curve which is the red curve here. It was the plot where we moved the window and for the coefficients. Now we see that the phases of them align pretty well. So this says that the primary peak here, where our correlation is maximizing, there we find maximum, the clouds are transported maximum northward. So since these peaks align so well, this provides a physical basis for our computed R. And also we found a secondary peak here centered around 20 local time. This also aligns with the second peak in the weighted mean latitude. So we can say that a combination of the wind velocities and the weighted mean latitude, which represents the launch activity per site. So both these together can explain our correlation curve pretty well. Although one may argue that the maximum northward value is quite low. It's 44 degree north. It should reach 80 degree north. But that's mainly because MIGHTI can only observe up to 42 degree north. So we had a limitation there. We want to focus more on the phases, not on the magnitudes. So we just want to show that these occur at the same local time. Now, finally, we look at the data from temperature and water vapor data from MLS, and we use a model called the 0D model to compute ice water content and ice mass density. So the top panel is just to show that the July mean ice water content is well correlated with the July mean frequencies. In the second panel, we calculate the maximum ice mass density over July because we want to look at the brightest clouds that CIPS is most sensitive to. So we find a good correlation with maximum ice mass density too. The black curve in all the plots are PMC frequency. Now, at the values of maximum IMD, we read the temperature and water vapor to see how the temperature and water vapor of the brightest clouds measure up with our PMC frequency. They are the third and fourth columns. So we see that the water vapor at maximum ice mass density is much better correlated with PMC frequencies than the temperature at maximum ice mass density. And this is also because the temperature is pretty much constant. If you look at the right axis, the variation is just about 1 to 2 Kelvin. So this tells us that water vapor, not temperature, is predominantly affecting the variability of the frequencies of the brightest clouds at 80 degree north. And this is consistent with a study I mentioned here. Now, combining these three observations, we find good evidence for our maximum correlation here. Now, when we send this out for review, we did some revised discussions. I will just state them very briefly. We discussed a bit on how the observed water vapor injected by launches are more than enough to affect a variation of about 23 metric tons, which corresponds to the ice water content variations we showed before. So we just try to explain that this variation is a plausible amount even for smaller launches. So there is enough water vapor to cause this variation. And we also talk about some differences from mid-latitude studies. So since poleward transport at mid-latitudes and high latitudes are very different, so our local time window was different from that done by Dr. Stevens for mid-latitudes. We also discussed some methods that can drive vertical transport because CIPS or MLS cannot observe the vertical transport of water vapor from 105 kilometer to PMC altitudes. So we discussed that it can be due to sedimentation, downwelling, and diffusion. Now here, horizontal diffusion is a phenomenon by which the plumes spread over the latitude. And it has been found that this horizontal diffusion of exhaust plumes can be over 40 degrees of latitude. So though we found a very low maximum latitude of 44 degree north, if it diffuses about 40 degrees more, it can easily reach our desired latitude of 80 degree north. So even with limited wind observations, we can explain how the plumes can reach our desired latitudes. So in summary, we found a range of local times for which the correlation between the launches and frequency is the strongest, frequency of the brightest clouds. Then we show that for the same local times, the wind velocities can favor the maximum northward transport. So the plumes can reach the high latitudes. Then we showed that for the bright clouds at 80 degree north, the water vapor is modulating the PMCs more than temperature. So combining this, we can say that, hey, water vapor is affecting the clouds more. And part of this water vapor can be due to launches. And these plumes are transported maximum northward, as north as possible, in a range of local times. And at that range, for year to year, the correlation between launches and frequencies are also very strong. So with this, we propose that space traffic exhaust helps modulate the interannual variability of the bright CIPS PMCs at 80 degree north. And we just published this work on the July of this month. So yeah, we studied July PMCs and we also published it on July. Okay, now, and in the American Geophysical Union website, I found an article by The Guardian which mentions our research here. So that was a bit of a motivation.
true.
That's right.
Could there be a trend? Could the amount of water a rocket injects be increasing with time?
For that we
On
need
average?
to, yeah, on average we need to look at the individual injected, mm, how much each rockets tend to inject there. The data of how much rocket is injected is often, as we saw, were publicly unavailable mainly, but yeah, that can also be an angle of investigation. We can consider the water vapor, how much water vapor each plume contributes, and possibly plot it with the amount of water vapor available per year.
Yeah, I'm just curious, over 40 years, as we became more environmentally conscious, did we stop,
Yeah.
per pound of fuel, have we put less nasty stuff and more water so that it could be growing, right? Because you don't see a correlation in the early years than you do in the later years. Even when rockets are fewer, you see the most correlation when the rockets are least, which is kind of interesting.
Yeah, that's true. That can also be an angle of investigation. Yeah.
Other questions?
Yeah, what's the typical lifetime of water vapor in the mesosphere?
You mean how long it takes to reach?
Yeah, like how long does it stay up there until it either reacts with something else or broken apart by sunlight or?
Well, in most of the shuttle studies, they take around some took 10 days, some took 4 to 5 days to reach up there. Then yeah, I really don't remember numbers on the top of my head now, but there have been local time studies too. Some clouds have lasted for a few hours.
Okay.
Then the yeah, sorry, I don't remember the exact
You're
number, so I don't want to
different
claim.
questions, right?
Yeah.
So if you have a kilogram of ice, right, in the mesosphere, in the polar region, in the summer, how long will that survive? And then if you have a kilogram of water vapor in the mesosphere, in the polar winter, how long will that live?
I see.
Or
Well,
better yet, just in any phase, right?
Yeah.
How long will that water survive?
well, I remember reading of Dr. Dillon had showed that sometimes it stays for a few hours, sometimes it lasts up to 10 days, the shuttle plumes. So
Okay, yeah.
it can really vary. It really depends on the amount of injection.
You're still answering a different question,
Okay.
right? Water in the polar winter mesosphere doesn't matter where it came from.
Okay.
If you just place it there, it has an amount of time it's going to live,
Mm-hmm.
right? Now, what's happening when you make a cloud,
Mm-hmm.
right, is the water's condensing on something, goes from vapor to ice, tends to become larger and sink,
Right.
right? What's the temperature do when you go lower in altitude? Here,
In the mesosphere, it increases.
temperature increases.
Temperature increases.
Yeah, so ice particles get bigger, 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 sink lower, 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 get warmer, 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 and then they become vapor again,
Yeah.
right?
Right.
And then it's dynamics takes the water back up.
Yeah.
So in ice, it might only last hours to days, right? Because it's cycling around.
Right.
Cloud is unlikely to last
Yeah.
more than a couple days. Even that would be long. But the water vapor itself, right, is going to stay water in one phase or another, right? For how long? And what's its ultimate destruction?
Ultimately, it undergoes sublimation, and the water vapor, the clouds are destroyed by sublimation, and yeah, I think I have to think about it. I read it in Dr. Rapp's paper of PMC microphysics. It's yeah, I kind of forgot how clouds are destroyed, but I think he mentioned sublimation.
So, yeah, in sublimation, it's exactly what I said, right?
Mhm.
The ice grows and grows,
Yeah.
but as it grows, it has to sink
Mhm.
because of gravity. It goes down to a lower
Right.
altitude, higher temperature.
Mhm.
But that just changes the phase, right? So that cyclic process,
Mhm.
right, can go on and on.
Right.
What happens that stops that? And I keep saying polar winter, it's polar summer,
Right.
but what changes that? What breaks that cycle? It's only a summer phenomenon, right? So
Mhm.
what happens in the fall?
Yeah, after summer, yeah, it then downwelling starts occurring. The mesosphere temperatures increase during winter. So yeah, so that again creates sublimation. Due to high temperatures, the clouds cannot nucleate
Yeah.
as efficiently anymore.
Terminal sublimation, right? So now
Yeah.
you cut off the upward flowing air that's
Mhm.
recycling. So once it
Yeah.
comes down and sublimates, there's
Oh,
no going
right,
back
right.
up. Right,
Right.
so it's a dynamics, right?
Yeah,
Whereas the
yeah.
atmosphere's rising in the winter, it's lowering.
Right,
So
right.
there's no way to.
Yeah, I apologize. It was there somewhere, but I couldn't connect it.
That's
Yeah,
okay.
Yeah, no, that's fine.
Yeah. And in the Lyman alpha, right, that destroys water.
Yeah.
So that'll give it a finite lifetime
Mhm.
eventually too.
Right.
Right, but most of that deposit's lower.
Mhm.
The only thing I was gonna say, it's not really a question, but I think, it's more of a statement that, the one part, sort of going back to the beginning where you're talking about actually the coldest temperatures happen in the, summer. Like
Mhm.
you get down to 140 Kelvin, that was more, I was sort of surprised by that, that's more the lowest temperature, but I guess it's all come from, maybe remind me, it's the adiabatic kind of.
Adiabatic
thermal-
cooling.
Yeah, the
Mhm.
cooling, okay, cool. Yeah. Yeah, that's an interesting thought, because, yeah, I guess my other question or sort of related to that was, these are always, or at least, from the ground, we see them in a visible spectrum, that maybe, they occur in the winter, but we just can't see them. But if it's not possible because that process isn't there, then, yeah.
And well, eyes, you might see them 50% of the time in a good July.
Yeah,
In radar, it's 100% of the
Okay.
time in the
Okay.
summer.
okay. Is that what the aim, is it more radar than like a visual, like that blue? Is that more radar or is that a visual measurement?
Well, AIM had 4 instruments initially. So CIPS is in the imager mainly. It observes at a single wavelength.
Okay.
I think it's 265 nanometer. Right? Yeah.
Okay.
Yes.
So in other words, you should be impressed when you see those AIM-CIPS images and you
Mhm.
see only the PMCs and not the blue sky.
Yeah,
You think that comes easy?
yeah.
I put years into it, and Justin Karsten's his whole life
Oh, wow.
into making that happen.
That's right.
My whole career, at least.
Is that Justin? Yes.
Yeah.
Yes. Okay. His professional life for
Yeah,
into making it happen, and it doesn't come easy. Would you agree?
not at all. It's that the Rayleigh scattering is brighter than the clouds.
Sometimes by 2 orders of magnitude.
Wow, okay,
So his hard work has gone to great use.
yeah,
Hard
Yeah.
work over many years. That's awesome that you're there. That's cool.
yeah. Otherwise, we can come up on, but any other quick questions?
That was fun.
Yes.
Thank you.
If not, thanks for joining us. I'm not sure that I have a speaker for December, but I'll look and see. And otherwise, I say have a good Thanksgiving holiday next week. And we'll see you back maybe in a couple weeks before the holiday break.
Sure.